Welcome to the another class of design of RCC structure. In this class, you are going to learn design of column which is subjected to combined axial load and biaxial bending moments. This is a continuity lecture of axially loaded short column. Exact design of columns subjected to combined axial load and biaxial bending moment, which is very complicated and extremely laborious. To simplify the process, IS 456 permits the design of such columns by following the equation of clause number 39.6 of IS 456 2000. So, whatever written here in this note is based upon clause number 39.6 of IS 456 2000. So, let us check out this clause in IS code. Here is clause number 39.6 of IS 456 2000. Members subjected to combined axial load and biaxial bending, which is the topic of this lecture. Let's read out whatever is written in clause number 39.6. Design of column which is combined of axial load and biaxial bending, that is based upon this clause. The resistance of a member subjected to axial force and biaxial bending shall be obtained on the basis of assumptions given in 39.1 and 39.2 with neutral axis so chosen as to satisfy the equilibrium of load and moments about two axes. Alternatively, such member may be designed by the following equation. Within third bracket, mux by mux1 whole to the power alpha n plus muy by muy1 whole to the power alpha n is less or equals to 1, where mux and muy is moment about x axis and y axis due the design loads, and muy1 and mux1 is maximum uniaxial moment capacity for an axial load of Pu bending about y and x axis respectively, and alpha n is related to Pu by Puz, where Puz is equals to 0.45 FCK into AC plus 0.75 Fy into ASC. For values of Pu by Puz is equals to 0.2 to 0.8, the values of alpha n vary linearly from 1 to 2. For values less than 0.2, alpha n is 1. For values greater than 0.8, alpha n is 2. So, these are the limits of alpha n. Now, we will check out the design procedure of this type of column. Now, the steps for design of column subjected to axial load and biaxial bending. So, here are the steps of design. To start with, assume some area of reinforcement along with its distribution pattern. Okay. So, first of all, we have to assume the amount of reinforcement, mainly the percentage of reinforcement. Next step is we have to determine Puz from chart number 63 of IS handbook SP16 or from the following equation also. PUZ is equals to 0.45 FCK into AC plus 0.75 FY into AS. So, there are two methods to find out PUZ depending upon the availability of values we have for a problem. Okay. So, after that we have to find PU by PUZ ratio. So, it is clear that for design of column along with IS 456 2000 we have to follow also SP16 for few charts. Okay. Now, next step is determine mu x1 and mu y1, the ultimate uniaxial moment capacities of the column with an axial load Pu from the suitable design chart from SP16. After that, we have to calculate mu x by mu x1 and mu y by mu y1, and then from the chart number 64 of SP16 we have to find the permissible value of mu x by mu x1 corresponding to the mu y by mu y1 and pu by puz. So, from chart number 64 we have to find out the value of mu x by mu x1 depending upon the values of mu y by mu x and pu by puz. Okay. After that, if mu x by mu x1 is less than mu x by mu x1 value found from chart 64, that is the permissible value, then the section is safe and design is adopted. But mu x by mu x1 is more than, any case, mu x by mu x1, the value found from the chart number 64, the section is unsafe and hence it is to be redesigned. Okay. So, these are the steps. Let us check out a problem. We will solve a problem of RCC short column with axial load and biaxial bending. Then it will be very easy to understand the steps and the considerations of IS 456 and SP16. Let us start to solve a problem. Let us first read out the problem carefully. Design a short column of size 500 by 600 mm, subjected an axial load Pu is equals to 2000 kilonewton and biaxial bending moment as follows: mu x is 200 kilonewton and mu y is 120 kilonewton. Use M20 concrete and Fe 415 steel. Okay. So, the cross section of this column will be like this as you see in your screen. This is the x axis and this is y axis. Okay. So, let us start the solution. What is given? Width is 500 mm with respect to x axis. Okay. Capital D, depth is 600 mm. Pu, axial load, is 2000 kilonewton. Mu x is 200 kilonewton meter. Mu y is 120 kilonewton meter. FCK is 20 Newton per millimeter square and Fy 450 Newton per millimeter square. Now, assuming that the moment due to minimum eccentricity is less than the given moment mu x and mu y, assuming 20 mm bars equally distributed on all the four sides of the column with an effective cover of 50 mm. That means small d dashed is equals to 50 mm. Now we have to find out a ratio, that is d dashed by d is 50 by 600, that is equals to 0.083. Now we have to start with assuming the percentage of steel. We assume the percentage of steel as 1.2% for the first trial. So P by FCK is 1.2 by 20, that is equals to 0.06. Okay. So now we have to follow chart number 44 of SP16. So d dashed by d is 0.083. So we can assume d dashed by d as 0.1. So chart is to be considered depending upon the value of d dashed by d. So we have to find out ultimately mu by fck bg square from that chart. Depending upon the value of d dashed by d, the chart may be changed. It may be used 43, 42, 45. That is depend upon d dashed by d. Okay. Let's check chart 44. Look, this is chart number 44 of design aids, that means SP16. Compression with bending, rectangular section, reinforcement distributed equally on four sides. Okay. So for column, look, this chart is depends upon Fy 415 Newton per mm square and d dash by d is 0.1. Okay. If Fy or d dash by d if varies, in that case the chart will be changed. Mainly d dash by d varies, so depend upon that chart may be changed. You may use chart number 43 or 44. You will you have to check it out from this right top corner, what is the value of d dash by d. So from this chart, what we have to find out? Look, in y axis this is pu by fck, you can see here pu by fck bd. This is a curved line of p by fck, and in x axis there is mu by fck bd square. From this chart we have to find out mu by fck bd square. From this equation, the value from the value of this equation we can easily find out the value of mu x or mu y. Okay. So first of all we have to find out therefore p value of p by fck, that means percentage of steel by fck, and in y axis pu by fck bd. So first find out these two values. So let's see. So for now d dash by d is 0.1, and now we have to find out pu by fck bd. Pu is 2000 into 1000 by fck is 20, b is 500 and d is 600. So that is equals to 0.333. Now p by fck is, we know, we have already find out p by fck, that is 0.6. So now we have to find out mu by fck bd square from these two given data. P by fck is 0.06 and pu by fck bd is 0.333. So let's check out chart 44. So in curve line from bottom 1 2 3 4, number 4 curve is 0.06. you can see here this is 0.06 and PU by FCK value is 0.333. so we have here 0.3, so it's like almost here. Okay, so now we have to find out the point which is belongs to 0.06 and 0.333. okay, so 0.333 almost is like will be there. okay, if it's cuts in 0.06 curve will be maybe here, and now we have to drag a line just straight below to this x-axis. So if we draw the line here, is almost just before 0.1. okay, so it may be 0.93 or 0.95. we can take the value of mu by FCK BT square. okay, from graph we can get the exact value, but we can get the nearest value. okay, so we can take mu by FCK BT square as 0.9395, such as like that. okay, so here you can see we take mu by FCK BT square as 0.095. okay, so now in your screen you can see the cross section of this column. okay, so there are two different side, one is 500, another one is 600, and there are two axes, x-axis and y-axis. so with respect to x-axis, small b width is 500 and capital D overall depth is 600, and with respect to y-axis, width small b is 600 and depth, overall depth capital D is 500. okay, so from this equation we can find mu x1. like if we put mu x1 instead of mu, then we can find out the value of mu x1. so mu x1 is equals to 0.095 into FCK, that is 20, into small b width is 500 into capital D square, that is 600 square. so this is equals to 342 kilonewton meter with respect to x-axis. If you calculate now mu y1, and the value of d dash by d will be changed, because small d capital G is 500 here. in previous case for with respect to x-axis, the capital D was 600, but in this case capital D is 500. so 50 by 500, that is also 0.1. so chart number 44 which we used earlier, that will be used now also. so all values will be same, that means mu by FCK BT square will be again 0.095. so if we put mu y1 instead of mu, so mu y1 by FCK BT square will be 0.095. so mu y1 is equals to 0.095 into FCK, that is 20, into small b, that is width 600, into capital D square, that is 500 square. Now this is equals to 285 kilonewton meter. Now we have to calculate PUZ, which we can calculate from chart number 63 of IS 450 from SP16, chart number 63 of SP16. Okay. Now percentage of still we know 1.2%. Fy is 450 Newton per millimeter square and FCK is 20 Newton per millimeter square. So we can get the value of PUZ by Ag from there. Let's check that chart number 63. Here is chart number 63 of SP16. So value of PUZ for compression member may be calculated from here. So there are two parts of this graph. In upper part, y-axis 100 As by Ag, that means percentage of steel, which is 1.2 as per our assumption, and this curved line is for Fy. So in our consideration, Fy is 415. So here 1 is marked and 2 is marked. There are 5 divisions. So next line, just top above the one marked, this line is 1.2. If we check where it is crossed with line of Fy 450, so this is the point marked black here. Now we have to draw a straight line, as you can see, to up to the curved line of FCK. In our case, FCK is 20. So here is also marked as dark. After that, draw the straight line up to PUZ by Ag. So 10 to 15, it is between 10 to 15. There are 5 divisions, so 10, 11, 12, this is 12.5. So PUZ by Ag is 12.5 from this chart number 63 of SP16. So now the value of PUZ by Ag is 12.5. So from this value we have to find out the value of PUZ. So in this step calculation of PUZ by Ag means cross area is 12.5. So PUZ is equals to 12.5 into 500 into 600, which is the lateral dimensions of column, that is equals to 3750 kilonewton. From this we can find out Pu by Puz. Pu is 2000 and Puz is 3750, that is equals to 0.53. So value of Pu by Puz is 0.53 and value of Mux by Mux1 is 200 by 342. 200 is given, 342 we have find out, that is equals to 0.585, and Muy by Muy1 is equal to 120 by 285. 120 is given in the value of Muy, and Muy1 we have find out, that is 285, that is equals to 0.421. Now we have to find out the value of Mux, the permissible value of Mux by Mux1 from chart number 64, depending upon the value of Pu by Puz and Muy by Muy1. Okay, so value of Pu by Puz is 0.53 and Muy by Muy1 is 0.421. So depending upon this, we have to find out the permissible value of Mux by Mux1. Permissible value should be greater than our calculated value to make the design safe. Otherwise, we have to redesign. Okay, so let's check chart number 64 of SP16. So this is chart number 64 of SP16 biaxial bending in compression member. In y-axis there is MUy by MUy1, so you have to check the value, check the point of the value which we have calculated of MUy and MUy1, and in x-axis there is, we have to find out the permissible value of MUx by MUx1, and in the curves is the value of PU by PUZ. So as per our calculation, value of PU by PUZ is 0.53 and MUy by MUy1 is 0.421. So value of MUy by MUy1 0.421 will be like here as marked in this page, in this graph, and value of this value, this line is cutting the curve of 0.53 almost like here as marked dark. Okay, so we have to draw a straight line through this. It is almost 0.8. Okay, so we can take the value of MUx by MUx1 as 0.8. Okay. So from chart number 64, the for permissible value of MUx by MUx1 is 0.8. So permissible value of MUx by MUx1 is greater than provided MUx by MUx1. Hence the design is safe. So the design is safe. Now we have to calculate ASC. So ASC is equals to P into B into D by 100, that is equals to 1.2 into 500 into 600 by 100, that is equals to 3600 mm square. So we provide 12 numbers of 20 mm diameter bars, so which ASC of is 3770 mm. Now design of ties. Diameter of ties should not be less than 20 by 4, 6 mm, and hence provide 8 mm diameter ties. Pitch should not be greater than least lateral dimension, that is 400 mm, 16 diameter of main bar, that means 16 into 20, that is equals to 320 mm and 300 mm. So we provide here 8 mm diameter ties at the rate of 300 mm center to center as shown in figure. Here is the figure. Thank you.